Alright, hello. In this video we're going to look at some very special types of problems called optimization problems. Get my pen working here. Come on, pen. What's going on? There we go. Okay, so these are what students often call word problems, where the idea is we want to maximize or minimize a certain quantity. So maximum, minimum, maximum, minimum, should be thinking derivatives, and that's exactly where this all fits in. So these are calculus application problems where we're finding a maximum or a minimum depending on what the problem is. So thinking back to related rates problems when we did our other example of what we might call word problems, what students often call word problems. The biggest challenge then and the biggest challenge now is in setting these up. So it turns out once we get our function set up, the derivative, the calculus steps really aren't too bad at all. It's the biggest work is in getting them set up. So also as with the related rates, all optimization problems are different, and there's no one algorithm that will work in every single case. Be that as it may, we can come up with a general problem solving kind of approach. That's what we're going to look at. So as just kind of a general strategy, first thing you do when you're looking at an optimization problem is understand the problem. That doesn't mean know the answer, just understand what it is you're looking for so you know where to kind of go in your next steps. So saying things, as simple or as silly as saying things out loud is oftentimes very helpful. I'm trying to find the minimum cost to make a box of these dimensions or whatever it might be. Something that's super helpful once you know what you're looking for, once you understand the problem, is to make a sketch or try to make a diagram of the situation and bring in notation for quantities involved. So if you've got a box-shaped object, you might have, L and W and H for the three important dimensions there, or whatever it might be. So then we're going to get to kind of the modeling phase of this, where you want to express that quantity that you're trying to optimize, that you're trying to maximize or minimize in terms of the other variables. So again, if it was that box example, if you wanted to, let's say, maximize volume, well, you would say volume is W times L times H if you were using width, length, height for the box dimensions. Now it's going to be different for every problem, but I mean it's something comparable to that. And then we're trying to set this up so we can use calculus ideas, and what we've looked at so far is calculus with functions of a single variable. So if we've got multiple variables floating around in there, we need to put it all in terms of one variable, and you're going to be able to do that with some of the information that's given to you. So this given information that I mentioned here in this step is often called a constraint. So for example, if we were trying to find the maximum volume of a box, you could just use infinitely long dimensions. You get as big as volume as you want. There's going to be some constraint that we have to deal with, like maybe we have so much, so many materials that we can use. The limit of whatever amount. So that's going to give you the constraint that's going to make this a kind of a real world problem that's going to have, the dimensions that maximize the volume is going to be a real thing you can find. Incomparable for any problem like that. So you got the quantity you're trying to optimize, and then you got some additional information you're going to bring in, get it into a function of a single variable. Once you got it as a function of a single variable, now you use calculus. What we've been talking about to find absolute maxes, absolute mins. The neat thing here is that you got a real world kind of application, getting your hands dirty type of situation where you can, maybe you're not actually literally doing it, but you can imagine this being a real world problem, rather than just saying, what's the local max of f of x, which is admittedly sometimes kind of boring. So that's the strategy. Not too much I could say other than that. So I had an example for you just to kind of walk you through the steps that I would follow if I was doing a problem like this. So we got our example. Find the dimensions of a cylinder of volume 32 cubic meters of minimal cost. The top and bottom are made of material that costs twice as much as the material for the side. Okay, so what are we trying to find? Let's try to understand the problem. I want to find the dimensions that minimize the cost. So it's an optimization problem where I'm trying to find a minimum value. It's going to be really helpful here to have a picture in mind of what it is I'm looking at. And Sketch doesn't have to be very good at all. You just have to know, good enough so you know kind of what you're looking for. So let's say we've got this cylinder shape here, and it's defining kind of parameters would be the radius, it's got a circular base, and then the height. So I've used R for radius, H for height. So I want to come up with a cost function. Now the cost is going to be cost of the side plus the cost of the top plus the cost of the bottom part, or the base. So I'm going to let P be the cost per square meter of the side material. Okay, so then cost is going to be, let me do a couple other things here. So I got my diagram here, keep it on the side. If I were to kind of decompose this, it would look like if I were to kind of take it apart and look at the amount of materials, I've got my radius of my circular, the base up there, the base down here, the lower base, R. This would be H, and this length would be 2 pi R, which is the circumference, like the round. So if I can imagine like making a cut here and unwinding or unraveling it somehow. So I want to know that area, and I know those areas. So it's an area problem, really, kind of a weighted area problem. So the cost of the side is going to be P, the cost per square meter of that area of that side material, which would be 2 pi R times H, plus the cost of the top. Well, it says the top and the bottom of the material costs twice as much, so that's going to be 2P times the top, which would be pi R squared, plus 2P times, again, pi R squared. So these are all matching up with what we've got up there. Alright, so that's P times 2 pi RH plus, grouping things together, 4 pi R squared. Okay, so we're kind of stuck there for a minute. I've got a lot of things floating around. Well, let's note the volume has to be 32. So here's my constraint. Because if I wanted to have minimal cost, I just make it as small as I possibly could. A fraction of a millimeter by fraction of a millimeter, whatever it might be. But I had this constraint. I need to be big enough so that it has a volume of 32 cubic meters. So using what we had, I need the volume to be 32 cubic meters for this object, this cylindrical object. The cylinder volume would be pi R squared, the base area times the height. So 32 equals pi R squared H, or H equals 32 over pi R squared. So that constraint is going to let me get rid of one of my variables, H. So now cost is P, that price per area of the side materials, times 2 pi r, whoops, 2 pi r times h, plus 4 pi r squared, which is P times 64 over r, so the pi's cancel, one of the r's will cancel, plus 4 pi r squared. Now the price per unit area of the side material doesn't really matter. It could be $1 per square meter or $10,000 per square meter. The dimensions that minimize it aren't affected by that. So this is really what we want to minimize. So let's give that a name. Let's say this is A of r equals 64 over r plus 4 pi r squared. We'll think of this as the weighted area. Because it's not quite the area. It's got that from that 2p, that twice as much for the base and top and the bottom. That's kind of built into it, so it's a little bit more than area. It's a weighted area. And now we can proceed. So now we're at this step, use calculus. We did all the hard work, now we're ready to roll. So we want to find r that minimizes that area. So we look at a prime of r, which is negative 64 over r squared. So the power rule on that one, plus 8 pi r. Now we want to find the critical point. Critical number is the language we use, sorry. So we're going to set this equal to 0 and solve. So I've got r cubed equals 64 over 8 pi, or just 8 over pi. And so my critical number is, only got one real root here, and that's cubic root of 8 over pi, which is 2 over the cube root of pi. So if we've set, this is our only possibility, if we've set this up right, this is going to be the dimension that minimizes that weighted area, which would be the dimension that minimizes that cost. We do want to check quickly. We could use a second derivative test. The second derivative is going to be 128 over r cubed plus 8 pi. And that is going to be positive. So this corresponds to a local min. It's the only one, so it would be our absolute min there over the region we're looking at. Okay, so if r equals 2 over cube root of pi, then h is going to equal 32 over pi times 2 over cube root of pi squared, which when all is said and done is 8 over cube root of pi. Okay. So cost is minimized when the radius is 2 over cube root of 3, which is about 1.37 meters, and the height is 8 over cube root of pi, which is about 5.46. And we're done.